All right. Took me a while to get the screen to come up correctly. We are recording. It is 11:02 on Thursday, the whatever today is, the 26th of October 2017. It's supposed to be linear algebra class, but I'm the only one in the room, so we'll get going. Hopefully some of the others will be coming in. Before I proceed too far on this, so let me just go through a couple of things. Number one, there is going to be tomorrow, Friday, at 10 o'clock, I believe it is, a UAB presentation. The theater department there is producing a Taming of the Shrew. That is a William Shakespeare play, one of his most famous comedies, and he had many really good comedies, and it's probably one of the top ones. It's going to be in the Birmingham East Campus. This is on Boston State Community College campus, East Campus, in the A.G. Gaston auditorium. Okay? That would be 10 o'clock tomorrow, Taming of the Shrew. Now, the original version that Shakespeare wrote had the woman being a very strong-willed, strong-minded, independent woman, and the guy was trying to tame this shrew. You know, they, I guess, were in love, but he was not able to handle her very well, and it made for quite a big comedy, okay, at the time. Well, as theater and artsy type people tend to do sometimes, they already don't want to do the same thing over and over, so they want to change things around a little bit. So my understanding, this UAB production, and who came up with it, them or someone else, I don't know, they're actually going to have the man being the obstinate, strong-willed, inflexible one, and the woman's trying to tame him. It's supposed to be just as funny, if not funnier. They promise a lot of laughs, a lot of play on words, a lot of jokes and things, Shakespearean type. So it should be quite a good performance in the A.G. Gaston Auditorium, 10 o'clock tomorrow morning. Now, I understand that some classes are required to take it, to go attend this. So it may be filling up, so you might want to get there a little on the early side to make sure you get a seat. I'm going to go over there on the late side of things just to make sure all seats are taken, or as many as possible, and if they need me to fill another seat, I will sit. But if the student's waiting to get in, I will give my seat over to them easily, okay? So I want the students to have the thing. I've seen a few Shakespearean things, and they're quite good. So I want you to have the opportunity to see that. Now, other issues that are on my plate, and I've been having a terrible car week. My car broke down on the way in on Monday, and by the time I got to call and try to figure out what was going on, I couldn't get a tow truck, couldn't get other things, so my wife came and picked me up Monday afternoon from work and went on from there. Tuesday, I had to get Uber in the morning because, no, that's not right. Yeah, I had to get Uber in the morning, and because my car wasn't working, I didn't even have it, and my wife couldn't bring me easily, so that was pretty expensive getting to work that morning, and late getting here because he was late getting to our place, so all that worked out poorly, but I got here. Wednesday, I had to hitch a ride with one of the other instructors who lives kind of out my way, and then thought I would have the vehicle. They said they just were waiting on a part, so they couldn't get it to me Tuesday afternoon, so I had to wait till Wednesday. Well, by the time they got the part, put it in and tested it, they said it would not work. I mean, the car would not run. I drove it there, but it would not drive home, okay? So my car is dead in the water in the Pet Boys parking lot. So I had to catch a ride home yesterday afternoon too, thinking I was going to be driving it home, couldn't. And today, and then this last night, we set it up for a rental car, and got the car this morning. Was late getting there because they didn't open until 7:30 in Southside Birmingham. Just a few minutes late getting here. But anyway, it has not been a good week, and my car is still over in Pep Boys parking lot, and I've got to find how to get it towed, where to tow it. We started the process on getting a different car. I have the rental car for a week while we try to work things out. So it's not, still got some insurance things to do and some other things. So it's not been all that great. So the reason I'm saying all that, my office hours are usually right after this class is over with at 12:15. I have lunch and then office hours from 1:15 to 3:15. But I may be on the phone, and if I'm on the phone, you can still come to my office. But if I have to leave campus, like to go over and take care of something at Pep Boys or somewhere else, then I may be off campus for some of either my lunch hour or office hours. But I'm hoping to be able to do everything by the telephone. So anyway, that's that. Tomorrow, then, I may still be taking care of issues. So I'll try to be on campus as much as I can between this will be on the Birmingham campus, 7:45 to 11:45. But it may be I'm going to have to go and be investigating a different car. Who knows what's going to happen tomorrow. So just warning you, if I'm not in the office when you come by, that may be where I am. All right. All that said, let's pick up with, I was hoping more students would come in. They're not here yet, so let's get on with linear algebra. We're in Chapter 3, Determinants, 3.1, Determinant of a Matrix, Example 6 at the bottom of page 109. Here is a matrix. And by the way, we talked about upper and lower triagonal matrices, which we had before, and we also talked about diagonal matrices. Okay? Example 6 is asking for the determinant of a triangular matrix. Here's a triangular matrix. Matrix A. 2, 0, 0, 0. Just for this, since they said it was a triangular matrix, or I said it was, that first row indicates it's a lower triangular matrix. Second row, 4, negative 2, 1, 0. Third row, negative 5, 6, 1, 0. I didn't do something right there. It's 4, negative 2, 0, 0 is the second row. My eyes drop down to the third row. And then the fourth row is 1, 5, 3, 3. That is a lower triangular matrix. Okay? What is the determinant of that matrix? Pretty easy to do. By the rule that we just did on 3.2, if A is a triangular matrix, which it is, of order n, ours is order 4, then its determinant is the product of the entries on the main diagonal. Just multiply those together. 2 times negative 2 is negative 4 times 3 is 12. Negative 12. There is the determinant. That's all you do, okay? All you have to do. Because if you were to do your determinants the way we have before, let's just do the first row because it has all zeros except for 2. That would then be the 2 here, positive 2, times the determinant of the matrix that's left here. Well, then you would just use the first row here because it has all 2's. It would be negative 2 times the negative 2 times the determinant here. Well, that would just be the first diagonal because the second diagonal is going to be 0. So basically you just did 2 times negative 2 times 1 times 3, which is your diagonal entries. Okay? Negative 12. Okay. That finishes 3.1. And I think I've already assigned most of these, but here they are again. Any of the odds, 1 through 11. Now, let me remind you again, why do I assign the odds? Because the two reasons. The odd problems, exercises, have the answers in the back, so you can check to see if you got the right answer. But if you didn't get the right answer and can't figure out why you didn't get the right answer, then if you'll notice that brown strip at the top of each page that has exercise at the beginning of the exercise, 3.1 exercises, notice the smaller print there. See www.calcchat.com for worked out solutions to the odd numbered exercises. So any of these you can't get the answers in the back and you can't figure out why you can't get the answer in the back, go to calcchat.com and see what they've and get some tutorial help for worked out solution in those exercises. If you still can't figure out why that's the answer, then bring it up in class, come see me during office hours, we'll work it out. So, any of the odds 1 through 11, do either 13 or 15 or both, do 17, do any of the odds 19 to 31, do 33, do either 35 or 37 or both, if you choose. Do either 39 or 41 or both. Do 43, it has 3 parts to it. Do either 45 or 47 or both. Either 49 or 51 or both. Do any of the odds 53 through 57. Do 59. Do any of the odds 61 to 65. Okay? Do 67 and or 69. And that pretty much winds it up. All right, so let's move on to 3.2. So let me erase the work I've got on this slide and let's look at determinants. 3.2 is determinants as elementary operations, and the first subsection is determinants in elementary row operations. Later we'll expand it to columns as well. All right. Here was the question. Here is a matrix, and you're trying to find its determinant. That's what the straight lines are for. 1, -2, 3, 1. 4, -6, 3, 2. -2, 4. 9, -9, -3. And 3, -3, 6, 3, -6, 9, 2. Okay, that's matrix A. Here's matrix B. I'm going to try to be a little more conservative in my writing here, because I need to get a 4x4 in here. 1, -2, 3, 1. 0, 2, -9, -2. 0, 0, -3, -1. And 0, 0, 0, -1. Which of those two would be, which of the following two determinants is easier to evaluate? Not A. A is no zeros in that one. You'd have to just pick any row, any column. I'd probably go with the first row and then start doing your cofactors and minors and all that kind of stuff and carry it on through. That will take you a while. Okay? B, on the other hand, is an upper triangular matrix. You know the determinant of any triangular matrix is the product of the diagonal entries. So yeah, I can look at that and say it's going to be 6, okay, without much effort at all. Now, the surprising thing may be to you the determinant of A is also 6. Okay? And how do I know that? Because I happen to know, if you'll notice, the first rows are the same. And if you start looking at this a little bit, you'll notice that the you can do some elementary row operations on A and get to B pretty easily. Okay? Now, you can't just do those willy-nilly and think you're going to get exactly the same determinant. You have to follow a few rules, and that's what we're going to talk about now. It says here, given what you know about the determinant of the triangular matrix, it's clear that the second determinant, the one we said B, was easier to evaluate. It was 6. Using the expansion of the cofactors, okay, to evaluate the first determinant is messy. Okay? So they show that process here. And when you do all that, you happen to come up with 6. Okay? Now, I'm not, really don't want to be about to do it. It would be long, arduous, not hard, but just long, lots of steps. They have the same value. Now, let's look at some of those elementary row operations. If you multiply the first row by -4, add it to the second row, then you get a 0, a 2, I think that actually comes out of -2. No, I'm sorry, a 2, yeah. -4 times first row plus the second row. It'd be a -8 plus, a +8 plus -6 is 2. -12 plus 9 is -9. Plus 3 is -9. And -4 plus 2 is -2. Yeah. Yes? Sorry, I just had a student who missed his class this morning. Found out he had a quiz and wanted to get a quiz, but I didn't have it in here, so I'll get it to him later. All right. So we did one elementary row operation there. Then to get the -2 in the third row to be a 0, you multiply the top row by 2 and add it to the third row, and that would give you a 0 in the first place, a 0 in the second place, a -3 in the third, and -1 in the fourth. Okay? To get a 3, I get a 0 in place of the 3 in the first element in the fourth row, multiply the top equation by -3, add it to the fourth row, and multiply the top row by -3, add it to the fourth row, and that would give you a 0. I hope I said -3. 0, 0, 0, and -1. Well, every operation we did was adding a multiple of one row to another row. And what we're going to learn right away, but fairly soon, is that elementary row operation does not ever change the determinant of the matrix. It leaves it the same as what it was before. Now the others will change slightly, not badly, but slightly the determinants. That one, however, adding a multiple of one row to another row never changes the determinant. So therefore, since you just did 4 of those, none of those change the determinant, then the triangular matrix you wind up with, really easy to do its determinant. Just multiply the diagonal entries together. All right, so let's look at a little more detail here. Example 1, okay. Is going to illustrate the effects of these elementary operations on a determinant. So let's clear the slide and move to this. Here is a new matrix A, and we're finding its determinant. And that's going to be the determinant of 2, -3, 1, 4. The determinant of that matrix is 8 minus a -3, which is 11. There's the determinant of that matrix. Now, what we're going to do to matrix B is start with matrix A and just exchange the rows. Make it 1, 4, 2, -3. Do its determinant, you get -3 minus 8, which would be minus 11. Okay? Now, at least for this example, and then we're going to extend it to all examples, anytime you interchange two rows, no matter what two rows it is, you're going to negate the determinant of your previous matrix. Okay? And this illustrates that. Changing the first and second rows gave you the negative determinant. Okay? So, starting with a different matrix now. So, I think that I will erase just the entries here. All right. Okay. Here it's happening again. My head is clogging up so badly I can hardly breathe. And here are we, merely 25 minutes into the class. This is ridiculous. Okay. But I think I may have to pause just a moment here and go get something, see if I can clear my head first and maybe get something to drink to loosen it up. So I'll be... All right, I'm back. Sorry about the delay. I couldn't clear anything. My head's so clogged up I can hardly breathe. But I did drink some fluids that hopefully will loosen it up a little bit. And I've also opened the windows. I think it's warmer outside than it is inside now, so this AC is blowing right on me, and there's no students in the room, so we don't have any added warmth. So maybe that will help a little bit. I don't know. If it's pollen in the air, which it could be, that could make things worse. So I hope it's not the case. Okay. Let's do another. The new matrix A is 1, -3. This is example 1B, 2, -4. Okay? Let's do the determinant of that. That's a pretty simple thing to do. -4 minus a -6, which would be +6, will be 2. Okay? Now, we're going to do a simple row operation here, elementary row operation. Multiply the top equation, the top row, by -2, add to the second. So we're going to leave the first row alone, 1, -3, and that would be a -2 times 1 is -2 plus 2 is 0, and -2 times 3 would be +6 minus 4 is 2. All right. Well, let's see what we got. Determinant of that would be 2 minus 0, which is still 2. Now that doesn't prove that that elementary operation doesn't change the determinant. It just shows that it doesn't. But remember the last one we did, that 4 by 4, we did 3 of those of that type of elementary row operation. And after doing 3 of them in a row, we still didn't change any. Again, it doesn't prove it, but it's a strong indicator that that doesn't change. All right? Sorry. At example 1C. Okay? Going to use the same setup, but different matrices. So just to recap, we see that exchanging any two rows is going to negate the determinant. Adding a multiple of one row to another row does not change the determinant at all. And this third one is multiplying the 3 elementary row operations, multiplying a row by a constant. Okay? So here is your matrix A that you're taking the determinant of. 2, negative 8, negative 2, 9. Okay? Now, when you look at that, if you were going to do a row reduction on it, what would be your first step? You would divide the top row by 2, or multiply by 1/2, making the top row a 1, negative 4. Leaving the second row alone, negative 2, 9. Well, on that top row, let's first do its determinant. I meant to do that first. 18 minus a positive 16 would be 2. Okay? Now do the one that we did, that simple row reduction, just dividing by 2. And you got 9 minus 8 is 1. So when you multiply a row, any row, by a number, C, K, whatever that number is, then the determinant of the first matrix is C or K or whatever times the determinant of the second matrix. Okay. I hope I said that right. If you multiply a row by a number, K, C or K or whatever, then the determinant of the first matrix, get the determinant of the second matrix, multiply it by that same number. Okay. Hope I said it right. All right, so that leads to theorem 3.3. And I'll write it down since I'm not sure all of you have books. And I'll write down in terrible shorthand. Okay. What we have are A and B are square matrices. Now, that does not guarantee well, let's say it this way. You can take the determinant of any square matrix. Okay? It's not guaranteeing it's a non-zero determinant, but it may be a zero determinant. But you have a square matrix. Okay. That's the given. First result. When B is obtained from A, capital A, okay, whatever I did didn't do very well at all, because harder and harder to read. When B is obtained from A by interchanging any two rows of A, okay, I'm sorry. I got off onto the proof of it here. When B is obtained from A by interchanging any two rows of A, then the determinant of B is equal to minus the determinant of A. They use the DET symbology. I like the straight lines. Okay, almost look like absolute values. They're not. Okay, number 2. When B is obtained from A, or go look, boy, that's ugly W. When B is obtained from A by adding a multiple when B is obtained from A by adding a multiple okay, I'm having so much trouble breathing, and that's affecting my writing. When B is obtained by adding a multiple of A, let's see. All right. A multiple of a row of A to a row of B, okay, all right, when B is obtained from A by adding a multiple of a row of A to another row of A, sorry, then determinant of B is equal to the determinant of A. There is no change when you do that elementary row operation. And third, this is the last one we did, when B is obtained from A okay. When B is obtained from A by multiplying a row of A by non-zero constants, C, then determinant of B is equal to thing keeps falling on me. This little, okay. Then the determinant of B is equal to C times the determinant of A. Yeah. Goodness gracious. Hands are cold from trying to write in this room. That's one reason my writing is getting so bad. It's hard holding the pen well. They do some theory proof here, at least of one of them. You're certainly welcome to look at that. But this theorem 3.3 provides a practical way to evaluate determinants. Do your row reduction, just keep up with what operations, elementary row operations, is doing. Multiply by a multiple of one row time, add that to 2 or 5 times to any other row, and you're not changing the determinant at all. However, if you do exchange 2 rows, you're going to negate the determinant, so keep up with that. How many rows have you exchanged? If it's an odd number, it's negation change. If it's an even number, you haven't changed it. Okay? And the third one, of course, is if you multiply any row by a non-zero value, that could be a fractional value or a whole number value, any kind of value, then you multiply the determinant of the original to that value by the determinant. Okay. So let's do example 2. Well, before we go to example 2, I think I was starting to read this paragraph before example 2. Theorem 3.3 provides a practical way to evaluate determinants. To find the determinant of a matrix A, use the elementary row operations to obtain a matrix To find the determinant of matrix A, use elementary row operations to obtain the triangular matrix that is row equivalent to A for each step in the elimination process. Use theorem 3.3 to determine its effect on the So, do your row operations, keeping up with what each one of them is doing to the determinant. And then at the end, find the determinant of that triangular form, which is just your diagonal element multiplied together. And then go back and do the changes, change signs or multiplying by a non-zero number, whatever ones you did, and that will give you the determinant of the next one. Okay. There's a little blurb here on page 113 about Augustin Louis Cauchy. Okay, he lived from the late 1700s through almost the middle of, or just past the middle of the 1800s. Now, if you want to sort of picture this historically, that's about the time between our Constitution and almost the beginning of the war between the states. Okay, the war with the British. I mean, we declared independence, of course, in 1775. I think it took us till about 1779 or 80 to finish the war, to have the peace come. And then we started with the Articles of Confederation and tried those for several years, and they just did not work very well. And they were working on the Constitution the whole time of that. Excuse me. And there's a little blurb here on Cauchy. And so he basically was about the same age as our country. Now, of course, he was from France, I'm pretty sure. And his contribution to the study of mathematics were revolutionary, often credited with bringing rigor to modern mathematics. He was the first to rigorously define limits, continuity, convergence of infinite series, those kind of things that we do in calculus a lot. So he did, like I said, sorry about my throat, brought much rigor to basically to calculus, okay? In addition to being known for his work in complex analysis, he contributed to theories of determinants, differential equations, and the interesting thing here, Cauchy's work, I think that's how you pronounce it, I've never actually heard it to catch how it's pronounced. I think it's pronounced Cauchy's work on the determinants preceded Cayley's development of matrices. Okay? So basically, I guess he was just using coefficients of the system of equations. Without actually forming a matrix, he was taking determinants. So I don't know exactly how he did it. That might be an interesting paper topic if that's your bag, okay? If you haven't already chosen one. So let's go to example 2. Find the determinant of this matrix. Here's matrix A. Not an easy 2 by 2 like we were doing, but 2, -3, 10, 1, 2, -2, and 0, 0, -3. All right. We want to find its determinant of that one. But let's get it to be a simpler matrix before we figure its determinant. First thing we would do if we were row reducing this was exchange rows 1 and 2. Okay? So this would produce a new matrix 1, 2, -2, 2, -3, 10, 0, 0, -3. Sorry. I wish something would loosen up, but so far it's not. All right. Now what did that do? This new matrix is negative. The determinant of the new matrix is negative the determinant of A. So what I'm going to do is, in parentheses, put a minus sign, indicating that's what that row operation did. Negated the determinant of the determinant of this matrix is negative the one of A, so A would be negative this one. Okay. Now, the next thing I would do is make this 2 a 0. And you do that by elementary row operation. -2, row 1, plus row 2. Okay? Now that operation does not change the determinant at all. So what the next matrix is then would be 1, 2, -2. You're using that row. 0, because negative 2 times 1 is negative 2 plus 2 is 0. Negative 2 times 2 is negative 4 minus 3 is negative 7. And negative 2 times negative 2 is positive 4 plus 10 is 14. And then you have a 0, 0, negative 3. Okay? We now have a triangular matrix, upper triangular matrix. We know its determinant. The determinant of this matrix here is 21. Okay? No change went from the previous matrix, but to get to that previous matrix from the original, we negated, so we know that the determinant of A was minus 21. Okay? Now, not that hard to do A. Take the third row here and find this determinant. Negative 3 is in a positive position, so it'll be a negative 3 times the determinant of this matrix here. And that would be 4 minus 3, minus 3, four and 3 is 7. Okay, so that's negative 3 times 7, and sure enough, that's negative 21. Okay, so yeah, its determinant is negative 21. Okay, now they did a couple of other things that there's really no reason why they did them. But they did a complete row reduction, not a reduced row reduction. They got it into row equivalent form, which meant the ones were there. You don't have to. All you need is an upper triangular matrix or a lower triangular matrix. We did upper and just multiply the diagonal. They went on to put all the ones to be where they needed to be. So sorry. And then multiplied. So basically all you did, and what they did, they wrote them in terms of the determinant, even though they're doing row reduction. And where I put the minus down here, they wrote them as determinants and just said the negative of that determinant. And that determinant turned out being 21. Negating that would make it negative 21. Okay. Several ways you can do it, but it seemed like to me they did a few extra steps that were not necessary. And then you have to go back and do the same calculations anyway. Now, we've only talked about elementary row operations till now. You'll notice the title of this section is elementary operations. And then the first subtitle was elementary row operations. We're going to introduce doing elementary column operations. And the Theorem 3.3, which was back there at the top of the previous page, 113, it talks about interchanging two rows, obtaining a new row by adding multiple of one row to another, or by multiplying a row by a non-zero constant. Okay? Well, everything we just said, if we could just take out the word row and write the word column, we've got it knocked. Okay? So, the 3.3 referred to rows, put the word column in there, you've got the same principles. Okay, operations performed on columns rather than rows of a matrix are called elementary column operations, and the two matrices are called column equivalent. Not row equivalent, but column equivalent. When one can be obtained from the other by elementary column operations. Okay. The following illustrate that. So let's do this example. And I am so sorry, my head is just... I can hardly breathe at all. And it's just such a pain in the neck. All right. Here we're going to have a matrix that we're going to do its determinant. 2, 1, negative 3. 4, 0, 1. 0, 0, 2. Okay? Now, we've found the determinant of that. This would not be hard to do a determinant. You got a row with only one non-zero entry in it. It would not be hard to do. In fact, let's just go on and do it just to show. This 2 here is in a positive position, so it's 2 times the determinant of the smaller matrix here, and the determinant of that matrix would be 0 minus 4, so that would be a negative 4. So 2 times a negative 4 would be negative 8. The determinant of that is negative 8. Okay? Goodness, I can't. Let me erase all that again. I'm having trouble with the pen. It keeps, well, it's a combination of a couple of things. Over the break in between classes, I took my other books out, and I usually use those to prop up the thing, and now it's flopping around on me. So let me get my pen back. This will be a 0 minus 4, that would be a minus 4. 2 times minus 4 is minus 8. Okay, that's a lot better. Having to hold the thing to keep it from flopping. So we know that determinant. But let's do a very simple elementary column operation. Okay? And what that column operation is, I'm going to draw this a little bit better if I can. Okay. If we exchange column 1 with column 2, just exchange these two columns. Now by doing that, that's minus the determinant here. And this will be a 1, 0, 0, 2, 4, 0, okay. Third column stays just like it was, minus 3, 1, 2. Sorry, I'm so used to pausing and letting people answer. I find myself pausing, and of course no one's in the room, so no one's here to answer. Well, now this is just simply an upper triangular matrix. What's its determinant? Multiply the diagonal entries. 2 times 4 is 8, and this will be minus 8. And there, the green is falling on me again and makes it look weird writing. So yeah, that gave us the same identical results. Okay? Okay. I guess this is a different, yeah, it is a different matrix, so let's do it. I should have just erased the things inside, but it's not hard to do this. 2, 3, negative 5. 4, 1, 0. And negative 2, 4, negative 3. All right. Now, goodness gracious, my back hurts. I guess from being chilled and holding myself too stiff all the time. Okay. If you are looking at this and trying to do row reductions, you don't have a lot of choices. Okay. You would have to divide, say, the first, I would exchange the first and third rows and then divide the new first row, the one that is in third now, by a negative 2, and that would give you a positive 1, negative 2, 3. And negative 3 halves. It would be dividing by negative 2. If you exchange the two rows, divide what was third row, now the first row, by negative 2, that would give you a 1, negative 2, 3 halves. And you still don't have a lot to work with, but at least you have a leading 1, even though it has fractional forms in it. So it's sort of a pain in the neck. But if you start thinking of looking at columns, notice that first column has a multiple of 2. So this is 2, say 2 and write 3. Good night. All right, that would be 2 times a 1, 2, negative 1, 3, 1, 4, negative 5, 0, negative 3. All right. Because you just divided that first row by 2, it almost looks like, and it's sort of what you're doing, you factored out that 2 from that matrix and from that first row. Okay? All right. Now, it looks like a pretty easy thing to do is then multiply the, let's see, do we want to do rows or columns? It wouldn't be hard to do row reduction now. Just multiply, add negative 2 times the first row to the second row, and just add the first and third rows, and you eliminate those 2. Okay. All right. Yeah, they do row reduction. Okay. Just wanted to make sure they were doing that. Usually if they start with columns, they tend to stay with it. I'm sorry, I'm looking at the wrong one. Oh, that's all they did. They just showed that. Sorry about that. So let's move on to example 3. I thought they were going to complete row reduction, or reduction in some form, but they did. They just stopped there. Okay. So let's move to example 3. All right. Find the determinant of this matrix A. All right. Negative 1, 2, 2, 3, negative 6, 4, 5, negative 10, negative 3. Okay, make sure I got it all right. I believe so. Okay. Well, just glancing at it, one obvious thing that comes to mind is you can factor a 2 out of column 2. Okay? So this would be 2 times the determinant of negative 1, 1, 2, 3, negative 3, 4, 5, negative 5, negative 3. Okay. So I'm doing determinants now, so I went from matrix notation to determinant notation. So I won't say equal, I'll just say it leads to that. Okay. Now, a pretty obvious thing to do now is add the first column to the second column, because they're exactly opposite each other. And that's not going to change anything, so this will be 2 times the determinant of, I'll leave the minus 1, 3, 5, and when you add those 2 columns together, you get a 0, 0, 0. And then it really doesn't matter what the rest are. 2, 4, negative 3, the determinant of that is 0. Okay? Because you have a whole row of zeros. Okay? So its determinant is 0. And they go into gory detail explaining that, but it is. You just go down that row and everything's 0. All right, there's a little linear algebra applied, which is something, if my wife followed this stuff, she'd love it, because she is a Sudoku aficionado. I can hardly ever do one, because she always does them as soon as she sees them, you know, and she's quite good at them. Okay, there's the number placement puzzles, Sudoku. The object is fill out the partially completed 9x9 grid boxes, blah blah blah. So if you're into that or at all interested in that, read this little blurb. Linear algebra applied might lead you to a paper topic, so I'll let you determine that. Okay, we've just got a couple more minutes. 5, it says. My watch must be faster than this computer anyway. Now it's 4. Let's just look briefly at matrices and 0 determinants. Okay? Example 3 that we just did shows that when 2 columns of a matrix are scalar multiples of each other, the determinants of the matrix is 0. That is one of the 3 conditions that yield a determinant of 0. Okay? So I guess I ought to write down this theorem, because I'm not sure all of you have books yet, so here we go. If A is a square matrix, and any one of the following conditions is true, then the determinant of A is 0. And any one of these 3 conditions true, then the determinant of A is 0. Okay, any one of these. First, an entire row or column, I'm going to put row / column without 2 L's. Okay, consists of 0. So if you just have a row or column of zeros like we wound up with in that one, you know the determinant is 0. But not only that, 2 rows or columns are equal, because then you can add or subtract one from the other and you get a row of zeros. Okay? Third, 1 row or column is a multiple of another row or column. Okay. So those are the 3. Any one of those is true, the determinant is 0. Now, you may have determinants being 0 in some other way, but those certainly would be. All right. 2 more minutes, 1 more minute. Let's just show 3 examples and we'll be done. The determinant of this matrix, 0, 0, 0. You can stop right there. It's going to be 0. 2, 4, negative 5. 3, negative 5, 2. It doesn't matter what those other rows are. If you have 1 row or 1 column of zeros, that determinant is 0. Okay? Secondly, if you have a matrix, 1, negative 2, 4, 0, 1, 2, 1, negative 2, 4, that determinant is 0. How do you know? 2 rows or columns are exactly the same. Okay? Or this matrix. 1, 2, negative 2, 2, negative 1, 0, and negative 3, negative 6, 3. Oh, 6. Okay? Well, if you look at these 2 columns, they're a multiple of one another. Negative 3 times the first column results in the second column. So that determinant is also 0. Okay? Now, I think we have hit the time limit. So, we'll start next time with example 4 on page 115. Sorry we didn't get further today. Let me erase previous stopping point. Okay. And homework exercises in this one, I think you can do any of the odds 1 through 19, I believe. And I think you can do either 21 or 23 or both. I think you can do 25, any of the odds 25 to 35. Okay? We'll hold off on that until next time. Okay? So, plenty to do, plenty to work on. Keep it going, keep the stuff coming in. By the way, I've gotten 1 paper, both of your first tests, but so far none of the second test. So keep stuff getting in. Don't get behind. We're already making progress in chapter 3, which is a very short chapter. We're going to be through with 3.2 and into 3.3, I think, next time. And then 3.4, we're not going to do everything in 3.4, but we're going to do quite a bit of it. So we're going to be through with chapter 3 fairly soon. Okay, so try to keep up and get caught up if you're not up. Okay, good deal. We will end